Hello everyone and welcome back. Now we made it. This is the last lecture in this series on data-driven dynamical systems. Now in this lecture I really saved my favorite thing for very last. We are going to talk about not only something that I personally have worked on, but something that I find to be one of the most exciting applications of autoencoders to dynamical systems analysis. And that is the integration of autoencoders with model identification, SINDy, right? So let's review a little bit, okay? Here's what we know. What we've learned over the course of this lecture series is a lot of the time I give you data, and we call this snapshot data, right? It's a bunch of snapshots of a dynamical system, and I typically tell you what's going to happen next, right? It doesn't have to be sequential data, but I do need to know that x1, its next instant in time is going to be y1, the state of the system. x2, its next instant in time is y2, and so on and so forth. So I give you this sort of organized data, and let's imagine both of these things are, say, like m-dimensional, and m could be relatively large, right? I'm going to show some demonstrations today where m is fairly small, mostly just to kind of explain the method to you. But I'm also going to put a link to a paper that I actually wrote where we have examples where m is very, very high or very complicated. And this thing is really sort of the method, the autoencoder is really compressing these things. But here's the thing. M-dimensional data, I have n instances of it. Now we remember how SINDy works, right? SINDy says, give me a dictionary. Right? SINDy says, give me a dictionary. I'll call it D, and it's a bunch of functions. I'll call it theta1 to theta k. Yes, I have k functions. And then SINDy tries to find a relationship that looks like this. It says, whatever is happening at time little n should approximately be a number, or in my case, maybe a vector, right? So we're using psi vectors. Theta1 of xn plus a vector to theta2 of xn all the way up, right? And really the goal here is to find those vectors that sort of best fit this thing, right? We've done this a few times. We know how to do this. We've seen a bunch of different applications of this, right? There's versions of this that are for SINDy, for EDMD, all of these kind of fun things, right? And I'm just going to put this underneath in a different color, right? I'm going to put little question marks. The whole goal is to find these things to best fit based on your data. Okay, so we know this, right? We're experts in data-driven discovery right now, right? Like we're really good at this. We spent a whole video lecture series learning all this stuff. Here's the problem. Okay? There are two major problems in applying SINDy or similar techniques. One, K needs to be huge. Okay? So maybe I have a very, very large and descriptive set of functions in my dictionary, and that's because I don't really have any idea of what should be on the right-hand side, okay? Then this thing is enormous, right? The number of unknowns that I need to identify is just out of hand. I mean, we could be talking about, for example, maybe M is a 128-dimensional system, right? Maybe it's a discretization of a partial differential equation in space, and then my dictionary is a whole bunch of polynomial terms in that discretization, right? This is going back to what we talked about with kernel methods, where the dimension here, the size of the dictionary, just blows way the heck up. So we could use kernel methods, maybe, but I want to talk about a different way to do this using neural networks. So we could have a very, very large K, or we could have a very, very small K. And in that case, you know, this one, let's just be silly here for a second. That makes me sad. That's just too much. I mean, it's going to kill my computer, right? For very, very small values of K, I like that, actually. I like that a lot. Why do I like that? Because the right-hand side is super simple, right? Maybe the right-hand side is just a sine function or just x squared or something like that, right? That would be amazing because I can work on that. I can sit down with pencil and paper and I can analyze it. But of course, that's almost never going to happen, right? In reality, things are not simple. So what we would like to do is we would like to use an autoencoder to address both of these issues at the same time. So let me show you what I mean here. We are going to use an autoencoder. So autoencoder. Now we're pretty familiar with autoencoders based on this lecture series. I'm going to take the function, the encoder. It's going to be from the original m-dimensional space into a latent space. I'll just call that r to the r. And then I've got a decoder, which takes me back out. And remember, we've seen this before. These things should have an inverted relationship between the two of them, right? But the goal is to have r small, and in particular smaller than m, right? So the basic idea here is maybe I have very high dimensional data, but there's a low dimensional structure sort of embedded in there. So you can imagine these things as projections onto manifolds, for example, sort of warping your data in such a way that it can be represented on something very low dimensional. But then inside the autoencoder, so inside what you want to do is do system identification. So system identification. So here is what you want. You want a new dictionary, which I'll just call it theta 1 tilde up to theta k tilde. And the hope here is that I can use less. These are all going to be functions in our r-dimensional space into R. And you're going to do SINDy, or do model identification. So model identification. You'll do model identification on the encoded data. So you're going to say, let eta of yn be approximately equal to, and here I've got I1 theta tilde 1 of eta of xn, and then so on and so forth. So plus eta of k, theta k, eta, sorry, not a row, eta of xn. So you do model discovery on the transformed variables. Now these pieces, right, all of these unknowns here, become variables for the neural network to learn during the training process. And the basic idea here is that you can hopefully choose a very small dictionary and let the neural network do the warping to best fit the dictionary, right? So it's a twofer that you're getting here. You get dimensionality reduction through the autoencoder, plus you get hopefully through the training process, an optimal warping and shaping of the data to best fit your dictionary. Let me give you like the simplest example of this, okay? Let's imagine you get data from this mapping. xn plus 1 is equal to sine of xn, right? We saw the sine mapping earlier. We saw that it's conjugate to the logistic map. Now imagine you just do SINDy, or good old-fashioned model identification, using a dictionary of monomials. Well, what's one thing you could expect? Well, I'm not going to get the system identically, right? Because I didn't put a sign in there. I didn't put the right-hand term in. If I put the right one in, I would be very happy if I put a sign in there. But good luck guessing that. So unfortunately now I'm stuck approximating it. Maybe I have like a Weierstrass approximation theorem I'm going to evoke here, or maybe just a Taylor expansion. That tells me the more monomials I have, the better the approximation. Lots of K's. Darn. Let's think about the alternative. I could train a neural network to warp the data. And in warping the data, I want it to best fit a dictionary of polynomials again, monomials. So instead, I could use the neural network to learn the logistic map. And if I could learn the logistic map, that's 2 polynomials. Very small k, I am very happy. And it's in the dictionary perfectly. So what does the neural network need to do through the training process? It needs to learn the conjugacy between the sine map and the logistic map, something we already know exists. And if it can do that, when it does that, it can fit my data, my transformed data, into this model. It can learn the coefficients, these 4s that sort of sit out in front of this thing. That's the beauty. It's doing 2 tasks that we value in mathematics. Reduced models in better coordinate systems, optimal coordinate transformations, and optimal discovery all together in one step. Let me show you an example before we go any further. Let's start with a demonstration on my all-time favorite chaotic system. I know that the right answer to this is supposed to be the Lorentz system, but my true favorite chaotic attractor is the Rossler attractor. It's this beautiful Mobius band structure that has all kinds of advantageous properties that I don't think are appreciated or taken advantage of enough in dynamical systems. So here is my plea for you to really care about the Rossler system. So I'll show you where this is going as we sort of walk through this. So again, here is the Rossler dynamical system. It's got 3 parameters, A, B, and C. A and B are typically fixed to be 0.1. C is the bifurcation parameter. When C is 18, we're in the really sort of fully chaotic regime for this thing, okay? So I'm going to simulate this up. I'm going to get some data. This is what the Rossler attractor looks like projected into the XY plane. You can see that it's sort of folded over itself. That's the Mobius band structure to this attractor. Otherwise, it would just be like a nice little ring pattern. But now you can kind of see this sort of folding happening. And if you plot this in 3D, it's because there's a big piece that comes up and goes around. But really what I'm going to do here is I'm going to look at Poincaré section data. And the reason for this is if you take a Poincaré section at x equal to 0, so that means you're really just tracking the y and the z variables every time they swing around the attractor, z basically goes through 0 as well, at least numerically. So you're left with a one-dimensional mapping of just what the y value is doing. So you imagine running around this attractor, you say y value is this now, run around, y value is this next, then the mapping that will iterate you through this we call the Poincaré mapping, right? So I've spoken about this in a few other videos. So what we're going to do is we're going to learn a conjugacy of the Poincaré mapping data. Might I remind you, this is truly data-driven. I have no idea what the function is that describes the Poincaré map. All I'm doing is gathering data from the system, and I'm going to apply my neural network in this thing to learn an optimal transformation of this to a system that I can analyze. Okay, so here, this is me tracking my Poincaré section data, and I'm going to sort of scale it into the interval 0 to 1 so that everything is just a little bit better behaved inside the neural network. Here, what I really want you to see is this is the Poincaré section data. So along the horizontal axis is what's happening now, and then you take a trip around, and that's what's on the vertical axis. This is just a function sketched down in data points. You can see that it almost has a sort of quadratic function looking thing to it. But you can see those arms are just a little too straight for that to be a quadratic, right? We're used to quadratics. They have this sort of cup shape to them. So it's not a quadratic function, and I'll show you what happens if you try to do a quadratic fit to that later. But what we're going to do is we are going to bend it and reshape it using the neural network to make it quadratic. So what I'm going to do is I'm going to use the autoencoder to transform the data so that it can be fit to a quadratic dictionary. And in doing so, basically producing a logistic map that describes the dynamics of this thing. So here's my neural network, right? We've seen this sort of basic autoencoder structure a few times. The only thing that's sort of new or interesting here is that there are trainable variables for the mapping. Let me show you. This was written up here. The latent mapping is going to be a quadratic function. We're going to force one of the fixed points to go to 0 so that we don't have to learn another like a C0 term here. C1xn plus C2xn squared. So those are going to be trainable network parameters. So again, the way this thing is working is it's warping the data in such a way that it can also learn the C1 and C2 to minimize that autoencoder loss that we learned about a few lectures ago. And so basically everything is mostly the same. Let me show you some nice results here before we or to proceed. So here's what we have. Basically what I have in red is the autoencoder representation of the neural network. And what I mean by this is just feeding it through the entire neural network. Where I am now, yn, goes all the way through the autoencoder structure to approximate yn plus 1. That is what's plotted in red. Black is the actual section data. So you can see that there's a very good fit, except for down here you can see a little bit of an error, but it's not too bad. You still get that sort of quadratic looking function here. Alternatively, if you tried to just take that Poincaré section data and fit a quadratic function to it, right? So use a dictionary that's just x and x squared or something like that, you can see this sort of junky fit right here, right? It completely misses that bottom portion, right? So where the autoencoder had a little bit of trouble, could probably be improved with training. Here we can see that it completely misses it and we get this junk fit. And this makes sense. The data is not quadratic, right? So we should not be expecting to just fit a quadratic function to this. Whereas the autoencoder warps the data in such a way that we can fit a quadratic function to it. And so one metric we can use to sort of gauge which one's better here, you know, other than just eyeballing this, is who does a better job of predicting into the future? Well, let's take a look at this. Again, black is the real data points. In this, we're talking about iterates through the Poincaré section. So one iterate going through, 2 iterates coming back around again, 3 iterates, so on and so forth. Everybody starts at the same point. You can see that the quadratic fit falls off immediately. Not surprising, we saw it was a terrible fit. Whereas you can see that the red autoencoder stays on till about maybe 6 or 7 iterates. Again, remember, this is 6 or 7 iterates into the future of the Poincaré section. That means that you are predicting it going all the way around the attractor and coming back, right? So in proper time units, this is a very, very long time. I think it takes about something close to 10 or 20 time units to traverse the attractor. So we're talking about 60 or 70 time units into the future that we're predicting the location of this thing, okay? Now let me show you one last example here. This one is slightly more complicated. This is the Gissinger system. So let me show you an example. Here, again, it's a 3D chaotic attractor. This one is much more complicated than the Rossler attractor. It has a lot more sort of folding that's happening. You can see. So here is the full 3D Gissinger attractor in blue. You can see the Poincaré section slicing through that attractor. It is a 2-dimensional section here. And each component of the map seems to sort of look like its own cubic curve. So what we're going to do is we're going to train up the neural network in order to take from 2 dimensions, compress it down to 1 dimension, and also learn a representation as a cubic mapping. And you can do this. The results are very, very nice. In fact, here's the cubic mapping that comes out of it. And once you've got a single cubic mapping, then I can sit and do my pencil and paper analysis, right? So here you can see that I've divided the mapping up by the critical points of it into 3 different intervals. And by dividing it up into these 3 different intervals, I can start doing symbolic dynamics. I can also start classifying the periodic orbits, right? We know that conjugacies preserve periodic orbits of a dynamical system. And so that means because I have a simple 1-dimensional system in the inside of the neural network, I do all my work in there, and then I use the decoder to lift it back up. And in doing so, I could start looking for periodic points of the Poincaré section. Periodic points of the Poincaré section represent periodic orbits of the full continuous time system that eventually come back on themselves after a certain number of iterates. And just as a last sort of maybe a amuse-bouche here, you can see that I pulled out a ton of periodic orbits from the Gissinger attractor. Again, it's projected into 2 dimensions here. But if you really want to see this, in blue superimposed across this are those unstable periodic orbits that foliate the chaotic attractor. So here's the shortest periodic attractor. You can see I have sequences based on the intervals, right? So which interval it runs through here, 0, 1, or 2, then where it's lifted to. So the sequence 0, 1, it is a periodic orbit in that original latent map that has one element in the 0 interval and one element in the 1 interval before repeating. And then so you can see some really complicated ones that come out of this, 1, 2, 1, 2, and 0, 2, 1, 2. You can see there's a very complicated unstable periodic orbits, but these things are the skeletal structure of the chaotic attractor. And so what this means is we're not only discovering maps that might be able to forecast, we are discovering maps that can actually analyze the original complicated system in a very simplified way, right? This is a reduced order model that describes a complex dynamical system. This allows us to extract structure and behavior from the system, something that we couldn't do potentially without the aid of the neural network. All right, with that being said, thank you very much for joining me on this entire journey through the contents of my book. If you have liked this, I urge you to check out the book where you can find much more detail than the things that I've spoken about here. You can also reproduce all of this using the code on my GitHub that is linked in the description to this video. And let me know if you end up applying any of this stuff to your own system. If you extend it, tell me about it in the comments. I really love to hear what everybody is working on. And I would love to hear if some of this is actually useful to you. So thanks for joining me. I look forward to seeing you in the next video lecture series.